Today's presentation is the first event of the 2019 SIPN-2 webinar series organized by Muyin Wang, member of the SIPN-2 project team. Our webinar, titled ICESat-2 over Sea Ice, Early Results, will be presented by Ron Kwok, who is a senior research scientist at NASA's Jet Propulsion Laboratory. A link to an online survey will be available at the end of today's webinar. Your feedback would be much appreciated. We'd also like to have suggested topics for future webinars. We have a couple housekeeping items before our presentation begins. There are two main viewing options available today: gallery view and speaker view. You can switch between those two views by clicking the icon in the upper right-hand corner, which is indicated by the red arrow. At the bottom of your screen is the chat button, shown here at the green arrow. You are invited to chat with other webinar participants at any time. To do that, click the chat icon and select the name of the participant with whom you wish to chat. There's also an option to chat with everyone participating in the webinar. The chat panel is also where you can enter questions for the speaker. Please type your questions into the chat window at any time. They will be addressed at the end of the presentation. For troubleshooting or technical help, please contact Stacy Stout via email. Her address is Stacy, which is S-T-A-C-E-Y @arcus.org. The SIPN-2 webinar event is organized by Muyin Wang. Muyin is a research scientist at NOAA and the Joint Institute for the Study of Atmosphere and Ocean at the University of Washington. Muyin, at this point, I'll turn the program over to you.
Thank you, Betsy. So it's a great pleasure for me to introduce Dr. Ron Kwok. My name is Muyin Wang from University of Washington. We will continue our bi-monthly webinar through the season, and the suggestions on the topics of interest are welcome. Please, you can email to me, muyin@uw.edu. And please do fill the survey at the end of the webinar to let us know your ideas. Thank you. So Ron graduated summa cum laude from Texas A&M University with Bachelor of Science, and then received his PhD from Duke University. He is an elected fellow of American Geophysical Union and the Institute of Electrical and Electronics Engineers. He has been a member of the ICESat-2 Science Definition Science Team since 2011, and also served in 5 other science teams currently. In the past, he served 14 science teams, working groups, and panels. He participated 3 field programs in the 1990s. He has received numerous awards and honors, and twice is a recipient of a NASA Exceptional Achievement Medal in 2003 and 2008. His research interests included the mass and energy balance of the Arctic and the Southern Ocean ice cover, and the role of sea ice in global climate, with current focus on analysis of thickness, small-scale ice, kinematics, time-varying gravity from various spaceborne and airborne instruments. Ron has 187 refereed journal publications, 1 book, and 12 chapters. His total citations more than 17,000 by now, based on the Google Scholar. What achievement. Now let's hear more about the ICESat-2 products from Ron. So go back to you, Ron. Thank you.
Okay, thank you, Muyin, for that introduction. I guess you can all hear me. Let me see if I can share my screen here. Here you go. And there. All right, so am I on, Betsy?
I believe so. Yes.
Yeah, okay. So thank you, everybody, for joining the webinar. I'm going to say a few words about ICESat-2 and sea ice, some early results that we've gathered since launch. Obviously, this is not solely my work, and a lot of that acknowledgement goes to the ICESat-2 team at Goddard Space Flight Center, and there are obviously a few individuals who spent a lot of time doing sea ice with me at JPL and at Goddard. So ICESat-2, so let's see, how do we, oh, there he is. I guess I've never tried it yesterday. I guess here, my arrows don't work. Okay, so I guess I got to do this. Oh, there you go. Works now. All right, so I guess ICESat-2. ICESat-2 is the next generation laser altimeter from space for NASA, and there are a number of data products which will be produced from ICESat-2, and I just want to list them here so that if that's of interest to any of you, you can look it up on the ICESat-2 website and talk to your colleagues about which products are of interest to you. So the products include land ice elevation, sea ice elevation, and freeboard. Those are the two cryospheric products that are of main interest to the cryospheric science community. We have also vegetation land height, ocean elevation, inland water height, and we do have atmospheric backscattering clouds. So those are the list of products, and there are a lot of actually interesting results that are that we've seen that you see when the data is released sometime later this month. And I'll say a few more words about the data release at some point at the very end. So ICESat-2 was launched in September 15th, 2018. So we're about 8 months, 7.5 months from launch. So we've made a lot of progress since launch in terms of getting the data, the altimetry data downlinked and analyzed, and so now we have some data products we can show you. So that the data collection actually started about a month after the launch. Was started on October 14th. So now we're in May now. So we have captured almost an entire growth season in the Arctic. So that's going to be of interest to a lot of us. And I'll show a few results about how the freeboard developed over time. And in the Antarctic, we captured the end of the growth season, October and November, and the beginning of the growth season this year. So that's a significant of interest to those of us who are interested in the Antarctic sea ice cover. And obviously, the data covers the entire. The LiDAR is on 24/7, so we capture most of the Earth as well. And there are a few gaps because very, very short gaps when we have to turn the LiDAR around to do different things for calibration and other things. But we have a very pretty continuous time series since October 14th. So what I'll cover today is this. The sea ice heights and freeboard from multi-beam photon counting altimetry, just to give you a little feel for what's involved and why it's different from ICESat-1 and from CryoSat-2 for those of you who are familiar with radar altimetry. And I'll show you a few examples of data that were analyzed from the Arctic and the Antarctic. And obviously the sea ice products, there are two sea ice products, a long track sea ice products that are of interest, and they're sea ice height and sea ice freeboard. and the data release is coming up, which I think a lot of you would be interested in. And I'll say some remarks as to where we go from here. So this is sort of where we started with a LiDAR in space. So so this is ICESat-2. This is Arctic sea ice thickness from ICESat between 2004 and 2008. So this is winter ice cover. So ICESat-2, ICESat-1 was not really designed to do sea ice. It was mainly dedicated to the ice sheet. At the time, we didn't really know whether we could do sea ice from ICESat-1. So ICESat-1 was a single beam profiler, so it's an altimeter. It gives you a profile along track. And the footprint was 50 to 70 meters, which is not really ideal for capturing leads that are required for calculating freeboard. And also the spacing between the spots are not, the spots are not contiguous. They're separated by 167 meters. So ICESat-2, as you'll see, is very different. It's actually designed for doing sea ice. So this is sort of where we're at in terms of getting sea ice thickness from LiDAR. And when I first started looking at ICESat-1, I didn't think that we were able to capture a significant decrease in ice thickness. In fact, what happened was between 2004 and 2008, there was this large decrease in ice thickness that we saw in ICESat-1, and that was quite remarkable because of the large changes during this first decade of the 21st century. And so this is what ICESat-2 looks like. ICESat-2 will has multiple beams, and it's a photon counting LiDAR. And I'll say a few words as to why that's special and slightly different from what we're used to in terms of thinking about altimetry. So there's 6 beams from 6 LiDAR beams arranged in 3 pairs. So there's a strong, within each pair there's a strong beam and a weak beam, and that's not used. I mean, it's not a requirement for doing sea ice. It's more a requirement for doing ice sheet, so that we can separate changes in height, separate changes in height from changes in surface slope. The footprint is repeated every 7/10 of a meter, and you can compare it to what we're seeing from ICESat with 167 meters. So and the footprint diameter is about 70 meters, whereas ICESat-1 is 50 to 70 meters. So that's a significant change in the way we can see the ice cover, as you'll see later. The footprints of 7/10 of a meter introduce a significant correlation between the footprints in terms of observing surface statistics, and that gives us a very, very high resolution description of the ice surface, roughness as well as slope. And the 70-meter footprint it's ideal. It's great for locating the sea surface within these narrow leads in the Arctic Ocean. So next slide is okay. So this shows sort of what multibeam photon counting altimetry tells us. So this is typically in a LiDAR, you transmit a waveform and you collect, you record the return waveform and you derive surface height from that. Whereas in the photon counting system, we transmit a bunch of photons from the LiDAR, and depending on the type of surface that we encounter, we get a few photons back, or we get many photons back. So if you have a relatively flat surface, depending whether it's specular or not, you get a very narrow band of photons back, and if you get a rough surface or a sloped surface, you get a spread of photons. Now, each of these photons in ICESat is for every photons event that's detected by the LiDAR, we calculate a surface height and surface geolocation. So each individual photon event is time tagged, so that we get an estimate of height and a height from the surface return. So this is sort of what it looks like from sea ice. So this is a photon cloud for a single beam. So as you're flying along the track, you get, so each of those individual dots, it's a photon. And so the surface itself, you can see the surface has a high density of return, and the photon, we get photons above the surface and below the surface because of solar background, and I won't explain that. But in any case, the surface itself is concentrated along that band of dense photon return in this photon cloud. So this is so each photon itself is geolocated, as I mentioned, and you can see the details in the photon returns from the surface. So the bottom panel just shows a blow up of what you see on the top panel here. So you can see that this is a very flat bit of ice here, and this is you can see these sort of ridge-like returns. I think they're from ridges, and here you can see sort of ice flow that's easily distinguishable from the flat surface along the track. So that's sort of what the photon cloud looks like. This is what we get back, and from here we analyze the data to get surface height from looking at the photon returns. So this is so what's important for the freeboard determination in ICESat. So the important thing for us is in particular, as I mentioned earlier, is getting a local sea surface in the narrow openings in the ice, in the leads and crack. So we can synthesize any sort of a spatial resolution that we want in terms of getting a surface height estimate. So in all the products that you'll see later on, each surface height is estimated from 150 photon aggregates. So we count 150 photons, and we use that 150 photons to calculate surface height. So this is what the 150 photon aggregate look like in this sort of a measure of the distribution of surface height from the photons, from the 150 photons. So in this case, the photon rate per shot back is about 7 photons. We get an estimate of the width, and it takes about 13 meters to come up with about 150 photons. So you have a resolution about 13.4 meters plus the size of the footprint, and then depending on the reflectance of the surface, we can get 150 photons over very, very short distance, or we have to integrate if you have a dark lead, for example, you have to integrate the over a longer distance to get 150 photons. So instead of having a constant spatial resolution along the surface, we get a variable spatial resolution, and that's very important if you use a ICESat-2 sea ice product. You can have resolution from 25 meters to a few hundred meters, depending on the reflectance of the surface. So this is sort of what the products would look like if you look for a long track product. So the first panel here shows the height. So these are the derived surface height. And the color here just shows the reflectance, expected reflectance of the target, of the surface. So this is brighter target here, and the blue is a lower reflectance target, flat, over a relatively flat surface. This is probably not a lead. This bit is snow-covered sea ice. And here you have, in this red bit here, you have a specular return from a very, very flat surface that returned a lot of photons back to the spacecraft, and so on. So this is the height profile that you see from ICESat-2. And if you look, the blue line plot shows the segment length, the amount of the width, the length of distance that's necessary, the distance that's necessary to come up with 150 photons. So it varies from about 50 meters up, 15 meters up to about 50 meters here. So the darker surfaces you have to integrate for a longer period of time to get the 150 photons needed to use to calculate the surface height. And so this is the segment length. This is background. Background just as a measure of if the sun's up, how much of the solar photons, how many solar photons is actually getting into the detector, because you always have a certain amount of bandwidth that the solar flux that's caused. You have solar events that's associated with reflections from the sun. And the bottom red plot just shows the number of photons per shot. So if you have, you can tell that if on a snow-covered surface, we're getting about 7 to 10 photons per shot, and it's pretty constant. And when you have a dark lead, for example, here, you have it goes down to a few photons, 2 to 3 photons per shot. So that's basically what we're doing in terms of getting a surface height. We get a surface height based on variable length segments, and we have taken into account the fact that you have a little bit noisier surface when the sun's up, and the photon rate gives you a measure of apparent reflectance. And so this is a broad description of what we get from ICESat-2 and how we get from the photons to parameters that are of interest to the sea ice community. And so just to show you how good the ICESat-2 LiDAR is. So these are 150 photon aggregates, starting with a resolution about 30 meters and up. And if you look at a very, very flat spot, this is as flat as we could find on the sea surface, on the ice cover. The precision is about 1.8 centimeters, and obviously there's some roughness in here that's contributes to the variability. But I think we're getting very, very close to about the precision of about 1.8 to less than 1.8 centimeters, depending on how flat the surface is. And also, so this profile is about 20 kilometers worth of data. And so this is very, very high resolution um, uh, coverage of the ice cover. You can see that these flat bits are thinner ice and weaker ice, and you can see these flows that sticks out into this from the surface, and so we can try. I mean, one thing to do is to we can, if anybody's interested in flow size, that these are actually very interesting. There's potential of actually getting flow size from this type of high resolution profile. So just to show you another few examples of what we can do in terms of comparing profiles from ICESat-2 with other data sets. So this is one example where the ICESat-2 orbit track crosses a MODIS image and a SAR image. I'm not going to show the MODIS image, but I'll show the SAR image, which was image about a little bit more than an hour after the ICESat-2 overpass. And this is in the with LC. And so this shows how well we can pick out features in comparing heights of thin ice in leads with what we see in the SAR image. So the yellow profile here is the heights retrieved from ICESat-2, and the red is actually the track. So the profile is displaced from the track. And so this bit here in the middle shows this relatively flat surface over in a SAR image, and we can actually see this sort of drop from discontinuity between the flow edge and the flat surface in this sort of really smooth flat feature, separating these ice flows between. And there are other instances where you can see that these ice flows are separated by this areas of thinner, weaker ice. And also this is another flow and going to here, another flatter surface here, and similarly for here. So this is sort of the type of resolution that we can see in the image. So this is very compressed. So that's why you see these sort of average areas of high variability within a flow So this is about 1.5 meters, and you can see these things have variability on the order of half to 1 meter or so. So that's very exciting in terms of seeing the type of roughness that we can just see in the ice data. Okay, so that was one profile, and this is some of you have seen this before, is sort of showing all 6 beams together in this transition from a relatively compact ice cover in the with LC going in toward the ice margin, where you have less compact ice and a little bit higher and a more thinner ice in the ice margin. So this is 6 beams. The red is the strong beam, and the blue is the weaker beam, and similarly for the 3 pairs. So you can see, so these are registered in cross-track, and you can see these sort of, you can see continuity of sort of leads and ice feature across track. And so there's a lot of details in that one could take advantage of in terms of looking at cross-track. So these beams are separated by, the beam pairs are separated by 3 kilometers, and within each pair, it's the pairs are separated by 90 meters. So there's very, very high correlation within the beam pair, and there's a little bit less correlation across the beam pair in terms of features. But on the whole, when we sample the ice cover on a broad, lower resolution basis, they should give you very consistent statistics when you look at a longer track and over the entire Arctic. So it's a challenge to try to use the resolution, but I'm sure a lot of you out there will be interested in looking at comparing ICESat with high resolution imagery and perhaps trying to figure out how to look at the correlation length scale in these features along track. So that was sort of a description of how we get heights and what we see in the data. So I'll give you some. So next, I'll show you a few gridded Arctic scale freeboard and how we get the freeboard from ICESat-2. Not in a lot of details. So most of you know what freeboard is. So this is how we measure freeboard. We get the local sea surface and difference it from the top of the air-snow interface. Now the difficult part that I haven't mentioned is going from height to freeboard. We need to know where the water is within the ice cover, and that's and so that eventually we can take the freeboard and convert it to thickness using the freeboard data from ICESat-2. So this is how we do this, and I just ignore the panel on the panels on the left-hand side. This is just to impress you. I can do this stuff. I can do block diagrams. But so the separation of ice and water sample from freeboard it's always challenging, but it's a lot easier in ICESat-2 because we have the resolution where we can see water surfaces in these leads, and just to give you an idea what we used to do that in terms of what ice parameters we use is we look at the photon rate. So we look at from each shot we get from an aggregate of photons we can get a sort of an estimate of apparent reflectance and surface roughness and background rate. So we use all these parameters within each aggregate to determine whether it's water or not water, and then we have surface type classification that's based on these parameters. So I'm not going to go into detail on how all this works, but suffice to say that these are for ICESat-2, some of the parameters are very effective in picking out open water, especially specular returns in leads that are brighter than the Lambertian surfaces that we typically expect snow reflectance. So next I'll show you some sample fields from ICESat-2. So this is the first sea ice freeboard that we produced a few months ago. I just want to show you this. This was exciting to me because it was done. Actually, when was it done? In late November. That was only about a month after we start data collection. So that was a significant accomplishment in terms of getting some geophysically meaningful data out to show that indeed we can do freeboard from ICESat-2, and you can see in this sort of gridded field that this is October 14th to November 28th. So this is a composite, and you can see the very thin ice out here, as the ice cover is growing in October. And I'll show a little bit more about the time series later, but this is this is a very interesting field that was produced early on. So here, one thing I want to show is we have 3 strong beams, and on an Arctic scale, these beams are very similar. As you can tell, this is November of 2018. This is beam 5. This is a strong beam, another strong beam, and the 3rd strong beam. So they are very, basically they're almost the same as the, if you look at the Arctic scale statistics, they're almost exactly the same. They're within the mean is within the centimeter, and the modes are within the centimeter. A lot, and if you do an average, it's very useful for minimizing noise, and also basically you're getting 3 looks at the Arctic at slightly different look angles, as well as statistics that are interesting if you want to look at variability over short length scales. This is an average of 3, and you can tell it's actually very difficult. You have to look very carefully to tell that they're different at this length scale. So this is where we at in March. So this is the ice cover. This is the Northern Hemisphere Sea Ice Freeboard in March, and you can compare with the coverage, the gridded coverage from ICESat-2. This is one of the strong beams with the gridded with the ice extent from passive microwave data. So you can see we have coverage all the way down to fairly far south here. And we can also see the little patch, a little bit of ice in the Baltic and the Barents and Baffin Bay, Hudson Bay. And this is a particularly low coverage year in the Bering Sea. We have some, but I assume that you will see a little bit more in April. But this is the Ice Freeboard over in March of 2019. So this is the ICESat-2 coverage of the Northern Hemisphere. Basically, we process all data within wherever there's ice. So if we look at the passive microwave ice extent map, and if there's ice there, we look for freeboards of sea ice in the ICESat data. So this is sort of so next, this one shows a time series of data since October. So this is October, November, December, February, and January is missing. We're filling that in as we speak, and this is March. So this is the scale of freeboards from 0 to 60 centimeters. Obviously, you can see the growth in the ice in the freeboard associated with ice growth as well as snow, and so this is sort of so the distributions here shows the freeboard distribution over time. So I'll just go through it one at a time. So this is October, and you have a very, so this mode here is associated with the thin ice out toward the margin, and this is the sort of the residual ice, the distribution from the old ice cover. And as we progress into November, now we have a much higher mode and a little bit thicker of this ice out here. And this mode starts moving, and all the modes start moving to the left, to the right, because of ice growth and precipitation. And so, and in December, as you move So one other thing I want to point out is that these distributions are scaled by the area of the Arctic. So the size of it is based on the area, and you can tell that these modes are going to move to the right as well as and the distribution, and the tail of these distributions is going to move to the right as well as the ice because of thermodynamic and dynamic redistribution from ice that's created early on in the season. So this is February, and this is March. So this is sort of what I have so far. We're processing a lot of data right now and getting the data ready for release late on this month. So this is so you can see that this is the growth, especially evident in the first year ice. The growth in freeboard, especially evident in the seasonal ice zone. So that was the Arctic, and this is an example of the Southern Ocean sea ice cover. This was in November of 2018. Actually, this was very interesting to us, to me especially, because you can actually see. We've seen this in ICESat as well as CrowdSat, but I think we can see the much thicker, higher freeboard in the Weddell Sea, much higher freeboard in the Bellingshausen and Amundsen seas, and very, very thin ice, very, very low freeboard, away from these areas where you have older ice and significant deformation and and higher freeboard associated with deformation and other and precipitation. And obviously you also see very thin ice in the Ross Sea, as you expect, so this map will be especially interesting next year as the Antarctic ice cover grows over time, starting in March and into November. And it'd be interesting to see how the freeboard develops, especially in conjunction with CrowdSat-2 data. So this is where we're at in terms of ice thickness in the Arctic Ocean. So this is sort of we have a composite of everything from submarine data, from ICESat-2, CrowdSat-2, from IceBridge. So this is where you had this is sort of a time series from multiple data sets of ice thickness within this data release area, and we show that it's declining and it's sort of flattened out a little bit. And so ICESat-2 would add to the CrowdSat-2 and all the other records in the that's available to us. So just to conclude, so we have Multibeam Sea Ice Products. So the products from sea ice, the long track products, will have two things. We'll have sea ice and sea surface ice, and for your planning purposes, everything starting from October 14th will be released, probably before the end of May, or maybe early on in June, and all that data will be available at the NSIDC. So the first set of data that will be released will be between October 14th through December 27th, and then I think they'll, depending on how things go, I think the the project will add to that archive as soon as that first release is validated, or depending on how everything works out in terms of getting a lot of data out to the users, because these products are not small. They're pretty big products, especially if you're interested in sea ice heights. The Sea Ice Freeboard product, which I assume most of you will use, will be a little bit smaller and more manageable, but it will have all this stuff will have 6 beams, and so there are slight differences between the strong beam and the weak beams because of resolution, but it's more interesting to you, if you're interested at the very beginning, is to look at the strong beams first, because the weak beams will have slightly different resolution, and there are fewer retrievals because there are fewer sea surfaces within the weak beams. So there will be gridded monthly sea ice. There'll be gridded sea ice freeboard products as well, but that will come a little bit later, and there'll be gridded sea surface height products, which will also come later. The gridded sea surface heights will be sea surface height within the ice-covered ocean and not in the open ocean. There will be another product of sea surface heights from the open ocean as well. So these are the official products that are released through the NSIDC. There are a couple of research products that would be developed by Goddard, and they will be available at some point soon. I think there'll be an long track sea ice product, and there'll be a gridded monthly sea ice thickness product from Goddard. So for those of you interested in just thickness, I think you have to wait a bit, or you have to do it yourself. But I think it'll be available probably soon, before the fall, I assume. I think. So I think I will stop here. So thank you for your attention, and I will take questions. Oops.
Thank you, Ron. That was a great presentation. We have had lots of discussion in the chats panel, and I've tried to highlight some of the questions that came out. I think that there will be more going on. And a reminder to everybody, please, if you've got questions, type them into the chat panel, and I will try to read them. The first question came from Bill Sokeland at the beginning. He asking about the Greenland ice melt and why does melt areas peak in summer? And so I think that's a question that we may just direct to other experts on the sea ice project team. So another question, and this started some discussion, was from Mark Drinkwater. And he asked, what is the underlying reasoning of the 150 photon aggregates? Is it because 150 gives something equivalent to a sampling along the track? And there was discussion following that, but I thought I'd let you respond to that.
Okay, so the reason for the 150 photons is to get us to there's an uncertainty in height associated with each photon, and the 150 photons are needed what we estimate needed to get to a precision of 2 centimeters. So it's basically 1/√n type calculation for a reasonably distributed surface relief.
Thank you. And a follow-up to that question was from Siri Joda Singh Khalsa, and he asked, this I think was from slide 9, which product is being shown where you're saying this is the surface of 5 to 50 meters?
Slide 9, actually, I was trying to figure out. Is this the slides?
That's the slide, right? I think that was the question that he was that the question was asked about which product is being shown here.
Oh, this is okay. So this is the sea ice height product, which is sorry. There are two products. I'll use the numbers. The sea ice heights will be in ATL07, which is the sea ice height product. You will have all the heights and all the information that's needed to produce the freeboard product. So this is you can find all this information, the height, the profile heights, the segment length, the background, and the photon rate in ATL07, which is the sea ice height product.
Thanks. I think there are two follow-up questions to that. Again, from Siri, are these photon elevations from ATL03 or derived heights? And so the follow-up is, can you only get freeboard during the polar daytime?
No. Okay, so there are a couple of questions there.
Right.
So these heights are, okay, so you can see these photons here. These are the geolocate photons from another ICESat-2 product, which has all the geolocated photons in it. And we use the geolocated photons in those products to derive the surface heights. So, in fact, I should mention that the photons themselves will not be available in ATL07 because there are a lot of them. It's trillions of them, and those files are huge, and so these are the heights derived from the photons. Okay, so that's one question. The other question was whether we can get photons whether we can get surface height when the sun is not up. The answer, yes, we do. The reason is that we provide our own illumination. The laser is transmitted, and we can see this. If the surface is visible, we can get it during the day and during the night. And the reason why I show this example here is that when the sun's up, you get a background contribution to the photon returns. So 5 megahertz is like 5 million photons per second into the detectors. And during the polar night, the background goes to almost zero because there's no solar illumination. In fact, during the night, we get a lot less noise contribution to the photon returns, and typically the retrievals are higher quality.
Thank you. Then there's quite a bit of discussion about freeboard, including snow, and I think the most direct question comes from Yangfei Zhang. How do you calculate sea ice thickness from freeboard? How do you deal with snow thickness?
Okay, so we obviously do not measure snow depth so there have been different approaches. One is use climatology, and typically that's been used for CrowdSat-2 and ICESat-2 as well and the second method is some of us have tried using reconstructions from reanalysis data. So some reanalysis products provide snowfall, and that's another alternative. The third one is new. In fact, that was something that of interest to us, and we've been looking into this, is to look at the difference between CrowdSat and ICESat-2 freeboards. And we've shown in the publication that indeed we could do that. So one of the things that we'll try to do is to calculate snow depth directly from two altimeters. So those are the current methods that I'm aware of. for getting snow depth and from space using for producing an Arctic fields of snow depths for calculating ice thickness.
Thank you. There's a question from, and there's lots of discussion in the chat that we'll try to capture, so I'm picking through things that look more like the questions that summarize that. This question is a little bit different from Doug. Can you provide an update on the status of the GRACE follow-on mission for Antarctic and Greenland ice caps? GRACE formally published results monthly prior to the end of the mission. GRACE FO was reported to operate in late 2018, but no results are shown on the NASA website.
Actually, I'm not up to date on what's happening with GRACE. So
okay, thanks. And then Mark Drinkwater just follows up with, we will have an Agora discussion session for the snow and sea ice theme at the Living Planet Symposium in Milano. So that's a plug for that. Siri asks again, thickness product with use data from other missions to estimate snow depth. So there's a follow-up question, I think, to previous answer.
Actually, I didn't quite get the question.
I'm not sure exactly. I think, Siri, I'll ask you to, I think we'll go on to the next one. I'll see if I can't follow up on that. Janet and Terry wants to know, are there plans to compare to the ICESat-2 data?
Yes.
Okay.
That's definitely something that we'll do. In fact, we have been doing that. We've looked at comparing thickness retrievals that with ICESat-2, and we also have compared. We will be comparing, especially sea surface heights, because we get sea surface heights from ICESat-2, and obviously ICESat-2 has been very successful with getting sea surface heights within the ice covered ocean, and those will be something that we'll be looking at carefully for validation of the ICESat products.
Thanks. I'm going to ask a couple more questions and we'll come to a close. Walt does a recap from Siri Jodha's comment saying that the data will be available from the NSIDC NASA DAAC website. There's a link on the website to sign up for the mailing list and get notification when the data is available, as well as later data updates. And Walt provides that link in the chat, which is nsidc.org/data/ICESat-2. Mitch asks, is there potential for ICESat-2 to provide freeboard or thickness data in the spring and summer months?
Okay, so there, obviously ICESat-2, it's a LiDAR, so it really depends on cloud coverage, because so that's of interest to a lot of us. If we can get any sort of summer coverage of the Arctic or the Antarctic. In fact, we have some Antarctic summer data now, so yes, we will be characterizing how well we can do the ice cover when it gets cloudy, as the season, when it's warm during the summer season. You know, obviously there's a lot more moisture in the atmosphere, and it's going to be cloudy. We haven't much experience with ICESat-2 because we haven't much experience with ICESat-1 because we never really collected summer data. So we will see how well we can do in the summer, and that largely really depends on cloud coverage and how well ICESat could do. The advantage of ICESat-2 is that we can integrate for a while to unlike a waveform LiDAR, we can integrate for a while to get a surface height estimate. So that may help us in the summer, but we'll see.
Okay, thanks. We're at the top of the hour, so I'm going to close the webinar and thank you. There are many more questions that I'm going to capture in a Word document and share with Ron and see if he has opportunity to respond back to everyone. It's been a really lively discussion on chat, and I'm so happy that that's been happening. I think there's been a lot of information, good information shared. I am going to ask you to, I'm going to share my screen now and ask you all to respond to the webinar, or respond to the survey that we mentioned earlier, and the link I believe is in, there we go, that took a bit. So thank you. I noticed that we will archive today's presentation on the ARCIS website, the SIPN website, but not until the data has been fully released from NASA. And we really would like to have feedback on today's webinar and the entire series. This short survey is really only 5 questions. So please go to this link at surveymonkey.com/r/SIPN2. I believe that is also available in the chat window. And we will also include this link for feedback in a follow-up email. So again, we want to thank Ron Kwok for a really excellent presentation, and also to Muyin Wang for organizing the whole series, and especially organizing this talk with Dr. Kwok. Thank you very much for your participation. This concludes our webinar.